Hi Calculus, we're on our final algorithm for curve sketching today, and I'm going to do this video in two parts. I'm having a little bit of problems with the tech. So here we go. We're going to do an algorithm, and I had been in a merge one day just for the fun of it, and I had noticed a sign up on the wall. It was very similar to this one, and it is an algorithm for someone in distress. And I thought it was a good example of what an algorithm is that we have to do things in a certain order, and we certainly can't skip any steps if we're going to do it properly. So we're creating an algorithm to sketch curves, which is maybe less life and death, but nevertheless we need all the pieces, and the order can be important. I have given you in your handouts a final algorithm. So I have 8 steps, I believe, yes, in my algorithm. You as a class tomorrow are going to spend a little bit of time creating an algorithm at the front of the room that you can have to refer to during tests and assignments in the final exam, so that we don't forget any of the pieces. And the order in this is rather deliberate as well. So you can use this as a template, or you can change it up a little bit, but we need all the pieces in order to sketch curves well. I will continue to refer back to that algorithm sheet. And so this is the order we're going to do it in today. Step 1 is we're going to look for discontinuities. So for discontinuities, there aren't any. It is a good idea to just make mention of the fact that you thought about it. And so when we continue to step 2, which is where we're looking for asymptotes, we know that there are no vertical asymptotes. This is not a rational function. For oblique asymptotes, we've been looking for where the degree of the numerator is 1 higher than the denominator, and it's difficult with our method. We're pretty sure it doesn't. And then let's consider horizontal. So as we look at end behavior, okay, as x gets more and more negative, e to the x part of it gets closer and closer to 0. So for the function, as x approaches negative infinity, the function itself is going to approach 0. As x approaches positive infinity, both pieces, the x piece and the e to the x piece, are both approaching infinity, so the function itself is going to approach infinity. So I suppose we should write that just a little bit prettier. The limit as x approaches negative infinity for the function does approach 0 because of the e to the x part. All right, so we've looked for discontinuities. We've talked about asymptotes. The third part is to have a look at our intercepts. Okay, what you can't see is that I can't reach the board because the mic is yanking my neck back. It's actually quite entertaining, but my my writing's going to be worse than usual. So our x and y intercepts, both, is 0, 0. You can discuss that if you wish, but it's not big deal. You have 0 times e to the 0, which is 0, so that is our x-intercept. For our y-intercept, we want to know where the function itself is 0. The only place that the function is 0 is when x is 0, because e to the x is never 0. Okay, upwards and onwards. Number 4. We are looking for critical points. And number 5 is where we classify them, categorize them. as maxes or mins or neither. All right. So I need to know where my derivative is 0 or undefined. So let's have a look at our derivative. The derivative of a product is the derivative of the first times the second plus the first derivative of the second. We could write that in factored form as e to the x, 1 plus x. That is not discontinuous anywhere. So I can look at where it's 0. It is 0 when e to the x is 0, which is never, or when 1 plus x is 0, which is when x is negative 1. So we have a critical point, negative 1. So I want to look to the left of negative 1, and I want to look to the right of negative 1, so that I can classify that critical point as a max or a min. So just looking at positive and negative values from the derivative, so this is where I'm looking. I'm going to choose a value less than negative 1. So e to the negative whatever, negative 3, is still going to be a positive number. E to the x is always above 0. But this bracket, 1 plus negative value less than negative 1, is going to be negative. So overall, my derivative will be negative. It's 0 there. If our value is greater than negative 1, that means my bracket will be positive, and e to the x is always positive, so that will be positive. So I've got decreasing, increasing, so this critical point is a minimum. I love it if you make a chart out of that. Way neater than I do. Okay, number 6 is our second derivative test. The second derivative test can help us find concavity. So for the second derivative, I need to be able to see my first derivative. There it is. I'm going to go, oh, it doesn't matter. I'm going to go with the one that's circled. So for my second derivative, I have derivative of the first times the second plus the first derivative of the second. So my second derivative, I could tidy a little bit. As having a common factor of e to the x, and one more of them. It should be e to the x 2 plus x. So for my second derivative test, I want to know where the second derivative is 0 or undefined. It is never undefined. So my second derivative is 0 when e to the x is 0, which is never, or when the bracket is 0, which is at x equals negative 2. My 7th step is to find a few key points. We already have the single intercept, 0, 0, but it would be nice to have some points in the different sections that we have looked at. So I would like to look at the critical point, -1. I would like the point of inflection, -2. And I'm going to do a point that's to the right of that, so I've kind of covered all the different sections. So if we use our original function, I have negative 0.4, and that's going to be our minimum. If I use my original function at -2, I get negative 0.3, and that's my point of inflection. And another point, the function at 1 is 2.7. So we have enough information here to draw an accurate curve. And so we're going to just put those points on as key points, and then be careful with our concavity. All right, here we go. We have an intercept of 0, 0. At -1, I have -0.4. Let's just spread this out a little bit. Okay. -1, -0.4. -2 is -0.3. Good job on lining those all up. 1 is 2.7. We know that we have a minimum. This one. And we have a point of inflection at that one. And so our curve would be, goes to the sky, because we looked at the end behavior as x approaches infinity. We know to the left we are going to be concave up until right there, and then it is going to be concave down, but we have a horizontal asymptote of 0. So concave down, to the best of my ability on a smartboard, would look like that.